Good afternoon. My name is Matthew Henderson. I'm a program manager on the Azure Functions team, and today we're going to be talking about something that might seem a little contradictory or counterintuitive. We're going to mix stateful and serverless. So, quick straw poll, how many folks here are already familiar with Azure Functions? Awesome. If you didn't raise your hand, I'm going to have a quick intro to get you up to speed. Okay, if you raised your hand, how many of you are familiar with durable functions? Okay, so we've got a lot of fun stuff to cover today then. There's been a lot of really great stuff happening around serverless and Azure Functions at Build in general. We're not going to be able to cover all of it. We're going to be focusing just on durable functions, stateful patterns, but I highly encourage you to check out all the other great content we've had at Build. Now, let's talk about what Azure Functions is. Azure Functions is a serverless function as a service platform. What that means is you're going to give us a piece of code, and you're going to tell us what causes it to run. Those events can be things like scheduled jobs, a timer, an HTTP request, a message going into a queue, or an image getting uploaded to a blob store. And then that causes a piece of code to run. And that code could be .NET, JavaScript, Java, Python, PowerShell, anything you want really. And that code is going to be handled by the platform. And of course we have ways of doing outputs, but the magical thing here is that at no point during this process do you provision, patch, scale, capacity plan, or otherwise manage servers. We're going to take care of all that for you. So as events come into the system, we're going to see how many events there are, and we're going to automatically scale your function to whatever load is required. And then we'll scale it back down as needed. The beautiful thing here is if you're running in the consumption plan for Azure Functions, you're only going to be paying for the amount of time your code spends running. No events, no charge. That's pretty powerful. But the actual event-based programming model is also very powerful just in terms of productivity. It's a different way of thinking about your applications and starting to build them. Now, when we start talking about this practice of building these functions, we're being event-driven. And really, whenever we're processing an event, we should really be doing one thing. Part of that's about resiliency, making sure that when if something goes wrong, you're able to actually handle things. You don't have these weird pipelines or things like that. Your functions should also be quick, especially if you're running in a consumption mode, right? We're going to charge you for the amount of time your code spends running, so make it as fast as possible, right? And then they should be stateless. So you really don't want, this is again dealing with resiliency. You can't be guaranteed that there's some state that's going to be preserved. At any given execution, it could run in the same space as your previous execution, or it could be on a completely new virtual machine. Or we could be taking away the virtual machine that was previously run on. These things happen in a serverless environment, so we tend to say, keep them stateless, quick, doing one thing. So now let's talk about durable functions. With durable functions, you can have orchestrations that do multiple things, and then have them be long-running, and they can have state. And so you may be asking yourself, did Matthew just contradict himself horribly in front of all these people? And to that I answered no, because there's a subtle distinction. Orchestrations have state. The individual functions that make up that orchestration, they don't need to, right? I can still keep them nice and stateless and have them be the things that I'm pulling around. But where I am in that process, that can be handled statefully. Long-running orchestrations are not the same as a long-running function. I can have functions that still execute within a 10-minute time boundary, but the overall orchestration could go to sleep, wait for external events, or any other number of things. We've got orchestrations that can go to sleep and wake up in a year, that kind of thing. So you can have these long-running expressions in your application, but the individual functions can still be quick. And the state, we talked a little bit about that just now. The state is where you are in the process of your orchestration. So what does this actually look like in practice? We want to see some code, right? So something like this. We have what's called an orchestration function. It's just a special trigger type, basically, or a orchestration context, rather. And the activity functions are the pieces that follow those principles we outlined earlier. An activity function is analogous to a typical Azure function. Just a piece of code that does something based on its input, gives some output. And I can actually, call these in sequence from within an orchestration function. That's pretty powerful. We're actually able to write code that actually describes the actual rules that we have for all these different functions. And how it works, we call it durable functions for a reason, because these things are resilient. They have state associated with them, and that state is where they are in their execution history. So we've got a slightly simpler hello world example here, and we're going to trace through it and see what's happening. So first, an orchestration function is going to get called. It's going to get woken up, and we're going to proceed through execution of those commands. Now, when it hits this call activity function part, it's going to actually check its execution history. And it's going to say, hey, have I run this before? Well, it turns out in this case, no. So we're going to go ahead and proceed and schedule some work for an activity function. And that activity function is going to wake up as the orchestrator goes to sleep. it actually does its thing. It goes back to sleep, and the orchestrator function is woken up again. So it proceeds to go through its execution once again. But this time, when it goes to the call activity async method, it checks its history, and it has a result. So it's able to proceed. And so the important thing here is the state is captured in that history table. The function itself is just basically querying a store. Now, you don't have to do that. The Durable Functions framework takes care of all the heavy lifting for you. But in that way, we can kind of reason about the state of where we are as really just a piece of data that we're interacting with. And we do that all the time, right? We write code that goes and calls into databases, deals with Cosmos, or talks into a blob store, those types of things. But we're just abstracting in a way so that you have this very productive model where you're just able to write code. So what does this allow us to do? Well, first we got to talk about what we can't do. So orchestration should have to be deterministic, right? Because we're going to replay. And that means if you're doing things like creating random GUIDs or calling out to other services with side effects and things like that, you can have a few problems. So we recommend putting all that inside of activity functions, and we've got a couple of wrapper functions that help. Also, infinite loops. An infinite loop is a really good way of making that history table get really large really fast. Not something you always want. So we have some patterns and practices around these specific activity functions, but it does enable us to do quite a bit of cool things. So one of the examples I used earlier was this pattern of function chaining. Now, I could write intermediate queues that go between my functions and pass things along, but this is a little bit more expressive, and I don't have to manage those queues, which is really nice. Serverless is about owning less, after all. We're trying to make sure that we can get rid of things that we don't need to maintain. So intermediate queues feel like a right candidate for that. So we have this ability to call an activity async. We're able to pass an input that we got from a previous step. We just have a nice sequence. Slightly more complicated, though. We can fan out pretty easily. I can write a message to a couple different queues and then have different functions that process things from the queues. The hard part is fanning back in. How do I, after all those parallel tasks have completed, go on to another step with just a single function? Well, in this case, we're going to create a bunch of these task objects, and then we have a task.winAll, right? And so this is the exact same thing as the call activity async in a way. It's saying, hey, I'm going to go to sleep now, and then when all these activities are done, wake me back up, replay my history, and I'll see, hey, I've done these before, that sort of thing. This is a very powerful pattern, right? This is how you can start getting like parallel execution really across events. Another one that's really common, asynchronous APIs. Somebody needs to post a job to something that you're writing, and that job needs to go and do a bunch of stuff in the background. Sounds like an orchestration. But you still need to provide status, right? I'm going to have a client that's sitting there polling and trying to see, is it done? That's something that we can provide out of the box. So you'll notice that the type of function here is slightly different. We have an orchestration client. That client is what we're going to be using to start an orchestration. So I can have any trigger and then have it go call an orchestration. After that, well, we can just actually respond to, in this case, an HTTP request with information that lets a client know how to actually go proceed with polling. It uses a location header, standard stuff. In a similar vein, we can have the functions actually be the thing that's monitoring some other system. And we can do that with notions of time. We can say, hey, we don't want to actually keep doing this forever, right? We want to know that we're doing some meaningful work and we're getting something done within a certain time. Otherwise, we might go through an escalation path. But we can also say, this orchestrator should really not do this like constantly. We don't need to be like destroying a downstream system by like hitting it with a while loop. So we can go to sleep. We can just tell the function, hey, wake me up after a certain time. We'll see if it's done. If not, go to sleep again. And similarly, approvals. Everybody loves approvals, right? This is how your manager makes sure that you don't have to pay for all the stuff on these nice trips, right? But in order to do an approval, we have to actually wait for some sort of event that tells us, hey, this orchestration can continue. And so for that, we have this wait for external event method. And similarly, we can set timeouts. So if our manager, say, doesn't approve things, we can go through another escalation path. So these are some of the standard patterns that we've had in durable functions since it's been introduced. Today, I'm introducing a new pattern, event aggregation, excuse me. The idea here is that we want to be able to deal with multiple events that are coming in and have them actually be composed. We want to treat them as a unit. We want to have some state associated with them. And the trick to this is, it's really hard to do concurrency, right? Because then we have to deal with all of these different events and we have to make sure that they're all actually interacting with the state in the right way. That's where our new friend, the entity trigger, comes into play. We're going to be talking quite a bit about this for the rest of the talk. So if we look at our portfolio of function types associated with durable, we have the client, that thing that actually lets us start an orchestration, works with any trigger. The orchestrator function, which is actually how we define in code all those things that we actually want to get done. And then the activity function, which is the unit of meaningful work that makes up that orchestration. Enter the entity function. And you can notice I've got these notes about stateless and stateful, right? Remember, the orchestrator is stateful in that it knows where it is in the process. But it's really state about the function itself, if that makes sense. It's really sort of metadata about your overall execution pipeline. With entity state, I'm making a statement about the actual things that I care about in my application. It's something that matters to me. And that's really powerful. It allows us to write much more complicated applications in a very simple way. So this is being packaged up as part of Durable Functions 2.0. So this is an alpha preview. It's a 2.0. That means it's going to have breaking changes. There's a couple other fun things along with that, though. We have stateful entities. This is the thing we're going to be talking about. And a new feature around locking in orchestrations. It uses entities under the covers. Well, more explicitly even. There's also alternate storage providers. Typically, all that history table and everything is using Azure Storage. We now have the ability to do it with Redis, which makes a lot of, say, running things on the edge much easier with Durable. So, durable entities. I like to think about entities sort of like I think about object-oriented programming in a way. There's a class, and that is something like a counter, right? And I might have many different counters, but this is like the overall picture of it, right? So I do have many different counters. These are the actual entities, and they have their own unique key and their own unique state. The way we interact with entities is with messages. And a message has an entity ID. You can see I've got the class and the key captured here. We also have the operation that we want to perform any other data. So what happens is when a message comes in, we use an entity function, that thing we just saw. And an entity function has a one-to-one relationship with the class. So when that function actually gets invoked, we're passing in a couple things. One, all the message information, but two, the actual state of the entity that was already there. And if the entity wasn't there, we create it on the fly. Now, this may sound familiar to some of you. This is very analogous to the virtual actor pattern. We're going to talk about why things aren't actors in a little bit, but it's way that we're bringing in actor-like behavior. So, what are the rules for entity functions? Well, they process one thing at a time. This is part of how we deal with coordination and managing the state. Like we just talked about, if it doesn't exist, we'll create it. You do not have to follow all the things we outlined for orchestrators, though. These can be non-deterministic. They can make outbound calls. They can do pretty much anything an activity function would do. There's also an important property. While an entity can invoke other entities, it's one way. You cannot wait for a response from a secondary entity. So let's take a look at that function that we just looked at a little bit more in depth. So first of all, we've got our entity context being passed in from the entity trigger, and then we're going to get state. So this is the typical loop for an entity function. I'm going to grab the current state that is available, and at some point at the very end, I'm going to actually mutate that state. I'm going to reset it. Now remember, we're doing these one at a time. They're serial execution, so that's how we are able to do that model. Then I process the operation, and we saw in the earlier example, like I was sending an add message, but I can send a bunch of add, subtract, all these things that I might do to a counter, and we will basically have a switch statement that lets us actually manipulate the object before we write it, commit it. And that's pretty much entities in a nutshell. Now, we have multiple operations, right? And so these are all modeled kind of as pure functions. So how do we actually start working with them, like from our other code? How do we send these messages? So here's a function that's calling an entity, and once again, it's an orchestration client. So I've got an event hub trigger actually bringing it up today. But what we actually care about is this part down at the bottom. I need to identify the entity that I'm going to be working with, and that's by class name and key. And then I need to signal it. I need to send it a message, and that message, is, again, the entity ID, the operation I want to perform, and any data that the operation needs. There's actually two different ways to do this. So first, we have to have the name, we have to have the key, but then we have this notion of calling. And calling is where we have a request-response pattern. This is something only orchestrations can do, but it allows you to actually wait for a response. That's that part that it matters for how we checkpoint things in execution history. Signaling, anybody can do. A regular function can do, as we just saw using an orchestration client. An orchestrator can do it. And this is also what entities can do for each other. So let's make it all a little bit more concrete. The past couple of examples that I've been doing have been sort of IoT focused. But another place where state really matters is actually in game development. And that's something you see with the virtual actor pattern quite a bit as well. And I think this is a fun way to just kind of explore a concept in kind of a light way. So we're going to go ahead and add area of effect to a little game. And for those who aren't familiar, area of effect is just the notion that I might have something that happens in, say, like a big old circle, and anything that's within that circle is subject to the effect, right? So we're defining an area for it. So let's take a look at how I might do something like that. So I'm going to hop over to our good friend Visual Studio. Can folks, whoops, did that not go? Sorry. Visual Studio. All right. Can folks see that in the back? Okay. So I have a standard functions project here. Nothing up my sleeve. The only thing is I now have a reference to Durable Functions 2.0. Now, I have a area of effect class, and I'm going to be just looking for an encounter. So, some set of situations where I might have an area of effect, and also something that actually originates it, a character that is creating the effect. We got a couple other metadata. Importantly, we're looking for, hey, if something is in this area, what happened? Is it in this area? Can we apply the effect to it? Well, in this case, I'm just returning true, but we would do that a little bit more in an actual implementation of a game. We'll get to actually how we resolve this. I'm using an orchestration to actually handle the resolution of the effect. But let's first look at the entities that are involved. So, one, I have the encounter itself. All this is just global game state that I might share. It might be available to all clients. So I have a list of participants, as well as a log of history. So all the characters that are in this encounter and everything that's happened to them. I've got a few helper methods to kind of make things easier, but here are the operations I'm working with. So we can add and check the list of characters. We can add stuff to the log, check the log, and then I've got a reset here. If I look at the actual handler, all we're doing, same loop. We're going to get the state. We're going to apply some of those operations, and all they are in this case is just some basic mutation and returns, and then I set the state. Now, the return thing is very important here. This is how we handle the call entity async method, right? This is where it's actually going to return the result. So let's take a look at character next. The character just has some identifying information, name, hit points, because we're going to be doing an area of effect attack. And we're going to have a location, so where they are. And that's how, when we're actually resolving the area, we're going to check to see, hey, are they in this area? I have a couple of helper objects here, but we've got our entity trigger here again. We're getting the state, checking the set of operations. So I've got a way of kind of initializing the character. I've got a way of getting their current location, very important for what we're doing. And then also very important, applying damage to them. So I'm able to go ahead and mutate the hit points metric, and then I'm going to return a message that basically tells me what happened. And then I'm going to be able to log that out. Now, I could actually just signal the encounter entity from here, but the reason I'm doing this is I may not want to have this message go out every single time damage is applied, so I want that to be subject to the rules of the orchestration. And then we set the state. And that's pretty much the gist of it. We'll get to the orchestration in just a second, but I do want to show you kind of how we're setting things up, because the demo here, I've got a couple of helper methods that we're going to see in a moment. So I've got HTTP triggers, and one of them is just using the starter to create a new orchestration that just sets things up. And our scenario here is we're adding a group of adventurers and a dragon, and the dragon is going to breathe fire at them. And that is the area of effect. Everybody who's in the cone is going to be dealing with some fire. So I also just initialize all the entities and things like that, just so that we have things to look at with our getStatus method, and we should talk about that next. So getStatus, just an HTTP trigger. It uses the orchestration client to directly interface with the state. So I've got this read entity state async method, and I'm able to get the encounter, and then I'm actually just going to log the log information back. So I'll hit this API, and we'll get the current log, the entire state of everything that's happened in this encounter. And then, of course, the most important part, we have to make the dragon attack. And so to do that, we have another API that's going to kick off an orchestration, and that orchestration is the area of effect resolution. So, very quickly, I'm going to go ahead and show you the area of effect resolution. We grab the input, we grab the list of all characters that are included, and then we take a lock. And that lock is something that we haven't talked about yet. but it's very important because I don't want to apply this if anybody, I don't want people to move out of the area and then not get affected, right? When I'm starting the resolution, I want to make sure that they are only in that location and their state is not mutating by something else. I have the ability to, I'm just signaling the log information, and I'm going to go through every single one of the targets, check to see if they're in the area, and then apply the damage, return the log state. So let's just go ahead and run this really quickly. And I realize I'm very close to time, so we're going to move very fast at this point. So we're going to run the functions core tools. So this is the exact same runtime that you get hosted in our cloud platform on your local box. We can see that I have my 3 APIs. Let's hit those really quickly. So I've got a create and counter API. Let's go ahead and get things set up. We're kicking off an orchestration. We can see some entities are actually getting logged. We've got the nice little entity notation. Let's go ahead and see what our status is. So currently, we have all the characters. Oh, that's really small, isn't it? We have all the characters in play. Now, let's go ahead and try our handy dragon attack. And we're going to see that we've got more state changes happening. It looks like I have a lot more log statements than I expected. So we've got those going. We're going to check that status one more time. And we should see that, hey, the dragon breathes a cone of fire. Everybody takes damage. Poor wizard. It happens. But anyway, that is us working with state. And we didn't have to do a whole lot to make it happen, right? We had to model things about our entity, and we had to do things like define the orchestration. But that was all business logic. That was all part of the game rules that we were defining. So this has actually made me very productive. Like that's the basis of a game going there. So jumping back to our slides just to wrap things up. We've got our orchestration locks. This allows us to coordinate across multiple orchestrations and make sure that they can't mutate entities in a bad way. It also allows me to associate 2 different entities that I might want to connect. I mentioned this earlier. It's not an actor model. It's very similar. This is how we're bringing actor patterns into functions, but a few important differences that you might get thrown off if you start thinking of it similar to your favorite actor framework. We model everything as pure functions. We have this durability over latency goal, and we cannot call another entity from another entity. This is how we prevent deadlock. So you can only do signaling. Preventing deadlock is a good thing. So what have we learned? State is a property of our applications, and we can write functions that interact with it. And there's 2 main types. One is progress through an orchestration of events that we define, and the other is actual things in our model, right? The characters in my game. That's state that I can manipulate. This is all available as part of Durable Functions 2.0. Please give it a try. It's an alpha, so maybe not for production use, but you can learn a lot about it, get started playing with it, and let us know what you think. There's plenty of other serverless sessions. This is the last one, but be sure to check the video on demand. And I just want to call it the service library. This is a great place for getting started. If you're looking for inspiration, figuring out what functions can do, the community submits all sorts of great stuff. We just revamped the site. But also, if you find a cool pattern and something you want to share, please pay it forward. This is a great way to facilitate community development. So thank you very much. I'm Matthew Henderson. Go mutate some state.